This video is all about benzene and why it's this structure instead of this structure. You may have come across this structure as the Kekule structure. And this is what people used to think benzene looked like. But before I delve into why it's this and not this, you need to understand some facts about benzene. There's a 120-degree bond angle. It's hexagonal, meaning basically has 6 carbons, so you can see 1, 2, 3, 4, 5, 6 in a hexagon shape. And just for future reference, this circle here represents a ring of delocalized electrons, which I'll talk about in more depth later. So now you know the basic facts about benzene, you need to understand that why it's this structure instead of this structure. And the first point is that benzene doesn't decolorize bromine water. So most alkenes, which this is, decolorize bromine water, so it goes from brown to colourless. But benzene doesn't decolorize bromine water. It doesn't decolorize bromine water. That's a pointer suggesting that benzene is not the structure. It doesn't have these alternating double bonds. Instead, what it actually has is a system like this. The next point is that benzene, all the bonds in benzene have been observed to be the same shape, same length, sorry. Now, it's well known fact that double bonds and single bonds are different lengths, the double bonds being shorter than the single bonds. So if we had this structure, the Kekule structure, with these alternating double bonds, all these couldn't be the same shape, same length, sorry, because double bonds and single bonds are different lengths. So this suggests that it's not this structure here. Instead, it's been observed that all the bonds are sort of an intermediate length between double and single bond. So length somewhere in between. Double and single. So the bond length have been observed to be in between double and single length. The next point is to do with hydrogenation. So if we think for a minute about cyclohexene, which say looks like this with one double bond here. If we want to hydrogenate this, we're basically removing this double bond, and what we get is a structure like this, with each carbon bonded to 2 hydrogens. So basically we're just adding 2 hydrogens, and the energy released from this is minus 120 kilojoules. So it's an exothermic reaction. So we would expect benzene, which the structure was thought to be like this, having 3 double bonds, we would expect this to be minus 360 kilojoules, as there's 3 times as many bonds being broken, and there's 3 times as many bonds being formed, so there's going to be 3 times as much energy released. But in actual fact, this is wrong. In actual fact, when you hydrogenate benzene, the amount of energy released, the enthalpy, sorry, is minus 208 kilojoules to the minus 1. So this suggests that benzene is much more stable. This suggests stability. Now, a term you should know for the exam is delocalization energy. Which basically is the difference between 360 and 208, which is actually 152 kilojoules minus 1. So this proves that benzene is more stable than it should be, basically, which proves benzene has this sort of ring of has a system, pi-electron system of delocalized electrons in the middle, which basically means that it's more stable, so more energy is required to hydrogenate it, and so less energy overall is released. This is all this is talking about. Less energy is released when you hydrogenate benzene than when you, say, hydrogenate the Kekule structure, than if you hydrogenated the Kekule structure, proving that benzene is more stable than expected. The last point as to why benzene is the modern structure and not the Kekule structure is that benzene prefers to react in substitution reactions with hydrogen, or not with hydrogen, but where the hydrogen atom is removed. Whereas we know from AS chemistry that alkenes, which we would expect the Kekule structure to be, prefer reactions with addition, where the molecule is added across the double bond. So the last point is that benzene reacts mainly in substitution reactions. Unlike alkenes. So to summarise, as to why benzene is this structure here instead of this structure. So the reasons are: benzene doesn't decolorize bromine water. Sorry, doesn't decolorize. Which suggests that it doesn't have this structure. This is the initial suggestion that it's not this Kekule structure. The next point is that all the bonds lengths are the same, with the intermediate length between double and single. Now, this is not possible following the Kekule structure because, as we discussed, double and single bonds are of different lengths. The next point we proved was the delocalization energy, and we took the example, say, cyclohexene. If you hydrogenate this, the energy released is 120 kilojoules to mole, as you're removing this double bond and you're adding two hydrogens. Whereas the energy released when you hydrogenate benzene is 208 kilojoules to the mole to the minus 1, whereas you'd expect it to be 360 kilojoules to the minus 1 because there are 3 times as many bonds being formed. And remember, when you form bonds, energy is released. And the delocalization energy is just the difference between the expected value and the obtained value. And this proves that benzene is more stable, and thus suggests that it has this delocalized orbital, or not delocalized electron system, in the center. And the last point we learned about was that benzene prefers to react in substitution reactions than most alkenes, which prefer to react in addition reactions. And the reason why it likes to react in substitution reactions is because it allows it to maintain the pi orbital system in the center, not in the center, around the ring, which allows it to keep stable. So by doing this, allows benzene to maintain stability of pi electron. Now, if you want to learn more about the bonding in benzene and this pi electron system I keep talking about, then you can watch another of my videos, which I'll be doing soon, about carbon double bonds and how they are bonding. So thanks for watching. Hope it's been useful. Thanks very much.